Okay, I wanted to do a video to finish up the 11.1 section. So we had gone through most of this last class. Okay, the important, the key idea was just basic probability questions. We went through several of these last class, and I think we had gotten all the way through to this section where we were going to talk about dominant and recessive traits. So I wanted to start there. So there's some problems you might find in homework that deals with these genetic diseases, or it might deal with like breeding plants to be a certain color. Um, so, as you go through this, just do a quick read of it to get the gist of what it's about. So this one is dealing with cystic fibrosis. It says it's one of the most common inherited diseases in North America, including the United States, occurring in about 1 of every 2,000 Caucasian births and about 1 of every 250,000 non-Caucasian births. And then we're doing a problem dealing with the genes that cause this disease. So the little c represents the cystic fibrosis gene, and then the capital C is a disease-free gene. And it says that this disease is recessive, which means only people who have both components, both of the cystic fibrosis genes, one from the mom, one from the dad, will actually wind up having the disease. So that means you'll have to have like two C's, two little C's. Such persons would ordinarily die before they're able to have children, but a child can inherit the disease from two parents who might be carriers of it. They're carriers of the disease. They don't actually have the disease, but they can pass it on to their children. Okay, so there's several questions related to that. So we're going to look at these. So this one says to find the empirical probability that cystic fibrosis will occur in a randomly selected infant birth among U.S. non-Caucasians. Okay, so it says that cystic fibrosis occurs in about 1 of every 2,000 Caucasian births, and then it says 1 of every 250,000 non-Caucasian births. So that's actually the probability written as a fraction. 1 out of 250,000 would be the probability if that an infant would have the disease. Okay, and then they said to 6 decimal places, so you would just take 1 divided by that 250,000. And I forgot to bring my calculator in here, but I think it turns out to be 1, 2, 3, 4, 5.00000, 5 zeros and a 4. Okay, when you divide that out. And so that would be the answer to that question. Okay. All right, now on part B of this question, it says, suppose that both partners in a marriage are cystic fibrosis carriers. That means they don't have the disease, but they have they're carriers of it. So this is what that means. So if you've never seen one of these, let me show you. So you can imagine having the mom and the dad. So this is like the mom, this is like the dad. Okay, both of them are carriers. Okay, so capital C is a disease-free gene. So the mom must have one disease-free one, and then little c would be the cystic fibrosis gene itself. And the dad would be the same way. So neither one of them have the disease, but they are carriers of it. So our job on this one is to construct this chart, which we're about to do, so we can determine the theoretical probability that their first child will have the disease. Okay, so when you look at this, if the child gets the capital C gene from the dad and the capital C gene from the mom, okay, that would be in that box. Or the child might get the capital C gene let me put them in the right order or the same order. The little c gene from the dad and the capital C from the mom. Okay, or they might get the little c from the mom and the capital C from the dad. Oops. I was trying to put them in the same order. Doesn't really matter. C from the dad, little c from the mom, little c from the dad, and little c from the mom. And the order you put them in really doesn't matter. The idea, though, is according to this right here, only these guys are going to actually have the disease. Then these two would be carriers of the disease. Okay, and then, but they'd be healthy. They wouldn't have the disease, they'd just be carriers of it. And then if the child were to inherit both of the recessive genes, then that would have the disease. So those are the 4 possibilities. And the theoretical probability their first child will have the disease is 1 out of those 4. Okay. All right, now on part C, we're doing a similar chart, but let's see what the deal is. Okay, so we have 1 cystic fibrosis carrier parent and then 1 non-carrier parent. Okay, so we have 1 parent that is a carrier, so that means they must have the little c gene. Okay, and then 1 non-carrier parent, so that means they don't have the gene at all. They're not even a carrier. Okay, so let's see on this scenario what would happen. So when we cross those two, here we would have 2 capital C's, 2 capital C's. Here we'd have a capital C in a lowercase and another capital C in a lowercase. Okay, so none of their children will wind up having the disease, but these 2 right here are going to be carriers, healthy, but carriers of it, not having the disease, but potentially being able to pass it off and create a child that does have the disease. And the question was, suppose a child is born to these folks, find the probability the child will be a healthy cystic fibrosis carrier. So that would be these 2 possibilities right here. So that's 2 possibilities out of the 4 possibilities, which means 1/2 would be that theoretical probability that the child will be a cystic fibrosis carrier. Okay. All right. And then one other thing in 11.1 I wanted to touch on has to do with odds and understanding the difference between odds and probability. They're related, but you just need to understand the connection and be able to change back and forth from odds to probability, etc. Okay. So let me blow this up a little bit. Let me see, I can just stretch it up. Okay. All right. So now we're getting into the section on odds. So say we have equally likely outcomes. So if all outcomes in a sample space are equally likely, and then we have this quantity of them that are favorable to some event. That's like, you'll see it when I do an example. And then we have the remaining ones, so this quantity of them that are unfavorable. Okay. Then we can talk about the odds in favor of some event being A to B. And the odds in favor would be A to B. The odds against the event would be B to A. Okay. Now, probability compares the number of favorable outcomes to the total number of outcomes. But odds does something slightly different. It compares the number of favorable outcomes to the number of unfavorable ones. Okay. And basically that's what's being said right here. So if you have the probability of some event being A to B, then the odds in favor of the event are going to be A to whatever B minus A would equal. Okay, that just sounds like gibberish until you see an example. Once you see an example, it's not too bad. So if the probability of some event was 2/5, and you need to get the odds in favor, the odds in favor, okay, would be 2 to 3. And the way the 3 came about is we took 5 minus 3. So it'd be 2 to 5 minus 3. So all it's, oh, darn it, I said it wrong. 5 minus 2 is what I meant. Okay, so let me say that again. All right, so if the probability of an event is 2/5, then the odds in favor would be 2 to 3. And the 3 came from taking the total number here and subtracting the 2 that were in favor. So what you're saying is 2 favorable, 3 unfavorable. Okay. All right, now let's suppose that you have something stated with odds. So let's suppose the odds in favor of some event are 3 to 7. Then you can convert that to a probability by remembering that the 3 would be what's on top when you do your probability, but you need the bottom part not to be the 4 and against ones, right? Not the in favor and that in favor and unfavorable, but you need those that are in favor over the total. So you would add the 2 is all that's saying. It just sounds hard whenever they do the symbols. Okay. All right, let's do a couple problems, and I think that'll straighten it out for you. Hold on, I dropped my pen. Okay, so let's look at these questions here. I think we did one of them super quick at the end of class, but I just wanted to look at them again. So here we have a spinner. It's going to be spun once, and we are interested in the event that the resulting number is odd. Okay, so we want the odds in favor of getting an odd number. So there's 2 odd numbers out of the 3. So the odds in favor of an odd number are 2 to 1. If we wanted the odds against an odd number, we would flip that around and say 1 to 2. If we wanted the probability of getting an odd number, then that would wind up being 2/3. See how you do it compared to the total. I won't erase. Okay. All right, now let's try this one. So here we have a person. Anne is choosing a ball out of a vase, an urn that has 4 red balls, 5 yellow balls, and 2 blue balls. We want the odds against each of these. So against red would be the other 2. So that would be 5 plus 2. That would be 7. So 7 of the outcomes would represent being against red. So 7 of them. And there's 11 all total, aren't they? But here we're doing odds. So we would say 7 to 4. The odds against getting a red ball would be 7 to 4. Okay. With blue, odds against a blue would be that you get either the red or the yellow. So that would be 9 to 2. Okay. Now, the odds against getting yellow or blue, okay, the odds against that would mean that you got the red ones. So that should be 4 to the total of these 2. So that would be 4 to 7. Okay. So if we wanted the probability of, not getting red, then it would be 7, but it wouldn't be over 4. It would be out of all total. So it'd be 7 out of 11. That's the difference. Probability compares the things that represent whatever you're trying to do the probability of, divided by the total number of outcomes. Okay. Where odds, it's the number that fit what you're trying to do, which is odds against red, not being red, that would be 7, to those that are red, okay, rather than the total. All right, so here's somewhere we're going to convert. We know the odds in favor of E are 10 to 3, and we want the probability of E happening. So we would say 10, but it would be over 13. We would add these two to get the total number of outcomes. Okay. The odds against event E would be 3 to 10, and the probability against E would be 3 out of 13. Okay. Right now, I put 4 on here because sometimes they'll give you the probability as a decimal, and if you need the odds in favor of this event happening, you need to understand what this decimal represents. So that's, if I read that correctly, that's 37 hundredths. That's really 37 over 100, that fraction. Okay, so the number on top is the number of favorable things in favor of your event. And when you're doing odds, you do the 4, the ones that are in favor, to those that are not E, that are against E. So what you have to do there is take the 100 in the denominator, which represents the total, and subtract 37 from it. Okay, when you do, you'll get 63. So you would report it as 37 to 63. Okay, would be the odds in favor of event E happening. Right? All right, and that's the end of 11.1. So I'm going to stop this so the video doesn't get very long, and then I'll look at 11.2 in a minute.